traditional view of algorithms, since most of you are like, so Pradisha told me that most of you are BTech and MTech. So what I'll do is I have toned down this particular talk, and this will not be a talk. You can assume that is just like a discussion in which I will also ask questions, and you are welcome to ask any question at any point of time. Okay, so just unmute yourself and ask me any question. Okay, at any point, because I cannot see you. I cannot see your faces, so I will not come to know whether you are understanding or not. So just unmute yourself and ask me any question. Okay, so this is the traditional view of of algorithms, where you have an input and you design an algorithm. You have some problem statement, and according to the problem statement, you get an input, and you have your algorithm which will run, and after some time it will give an output. Okay, and for some of the questions that you have studied in your bachelor's in the data structures and algorithms course is like, you have an array, you want to sort it. So you use a quick sort algorithm. So it takes any array as an input and it outputs a sorted array. Okay. Suppose in some shortest path problem, well, you are given a graph, which is the input, and you have to output the shortest path from S to any other vertex, and you use the Dikkstra algorithm. Okay. What are dynamic algorithms now? Okay, so in dynamic algorithms, the graph is not the graph. So let's not talk about graph. We'll come to graph, but the input itself is changing. Okay, so you start with some input, and for that particular input, you have some algorithm, and what for that algorithm you give some output. Okay, so this is your current output for the current input. Okay, and after this, what happens? There is some update. Okay, what is an update? Well, update is some change in the input. Okay, some part of the input has changed. Now, depending on what has changed, you have an update algorithm. You update your algorithm, or not, you have something in your algorithm which will update your output, and you will give a new output. Why? Because the input has changed, so your output should also change. For example, well, if you're solving the shortest path problem, well, suppose some edges are now not there, so they are changed. So you've deleted those edges. Now the shortest path changes, so your output also changes. Okay, and this goes on and on. Okay, maybe at next point, next update step, well, again there is some change in the input, and you have your update algorithm, which will again update something depending on what the change is, and give you the next output, and so on and so forth. Okay, so in a nutshell, what happens in a dynamic graph algorithm is, at each step, some part of the input changes. Okay, and you have to update your solution using an update algorithm. Okay, and this is basically what a dynamic algorithm is. Okay, now Pradisha was asking me that you have also learned about streaming algorithm, online algorithm. But let's take streaming algorithm. Can anyone tell me what is the difference between streaming algorithm and a dynamic algorithm? Since you have done streaming algorithm, some part of it yesterday. Anyone? What is the difference between streaming algorithm and a dynamic algorithm? So in the streaming algorithm, what happens? You get a stream. So this is a stream of input. Okay, and the thing is, you can read this. So you get this stream, and the thing that you do is you are reading this stream from left to right. Okay, and at the end you have to give the output. So for example, and the stream is so big that you can just read it once. So you read this stream once, and then you have to do some changes, and you have to throw this away. Okay, because you are going to read the next thing. The point is you cannot store all these, you cannot store.
Prashant Vaidya is saying only at the end we ask queries in streaming.
Yeah, I am not able to, why I'm not able to, okay, yeah, now I can. So as I said, you can just unmute yourself and give is a communication method which has a lag. Okay, just unmute yourself and give the answer. Yeah, so that is what I'm saying. Only at the end you have to give the answer. Okay. So this is the first thing. In the dynamic algorithm, you have to give answer at every update step. Okay, I mean you have to be ready with your answer. Okay, but in the streaming algorithm, well, you have to give answer at the end. The second thing about streaming algorithm, some of the streaming algorithm is that you cannot store the input, the whole input in your memory. I mean, this is one thing which on which your algorithm will be judged. Okay, so you are getting all this data, but can you store a small part of them and still give the answer? But that is not the case in dynamic algorithm. If you want, you can store all the data. Okay, but there is, in my view, there is a lot of similarity between streaming and dynamic algorithm. What I feel is that if you have a good streaming algorithm for a problem, then there is a better chance that there would be a dynamic algorithm for that particular problem, and vice versa. Okay, because the differences are not that huge. Okay, so what I'm saying, there is a lot of chances. Doesn't mean that you can always go from streaming to dynamic. Okay, but what I'm saying, that there is a chance. Okay, so I hope you understand what is the difference between dynamic and streaming. Okay, but now let me ask you a simple question. Have you ever come across any dynamic problem in any course that you have seen? I mean, I'm talking about basic courses like data structure algorithms. Has anyone ever seen a dynamic problem? Anyone?
Yes, sir. Like, I mean, we had seen the question where, like, the edges keep coming in, and basically we have to ask if there is a cycle, or if
So this is
it's a
where
redundant edge, something like that.
this is where in which course, or there was a talk like this?
Yesterday we briefly discussed on this, like.
But with Saket, okay, that is a hard problem. The edges are coming, and you have to find if there is a cycle or not.
Yeah. So
Right?
like.
Yeah, so that is a hard problem. I'll not even go to that problem. Someone else also had said, like matrix chain multiplication. Okay, okay. Is the input coming? Are the changes coming online in this problem?
So can we say that if we have a minimum spanning tree given and if we change some weight of a particular edge?
Yes, but that is only okay. Yeah. So that is one particular problem that can go well. I mean, that is one problem. That is, you are correct. In fact, this is a very famous problem. Okay, so what you have to do is you have to maintain a minimum spanning tree dynamically, and this is not an easy question. This is actually pretty hard. I mean, we still, I mean, in last 5 years, there were big papers on this particular problem. So yeah, so this is a problem. But what I'll do is I'll tell you a problem which is very simple, which is the following. Okay, so maintain a minimum in the array subject to following updates. Okay, what is the update? Well, add an element in the array, and the second update is delete the minimum. Okay, this I claim is a problem that you have seen many times. Okay, can anyone tell me how would you solve this problem? So I want to I add any element in the array. So you can assume all the elements are numbers, and I want to delete the minimum from this. So these are only two operations that that I want to do. How would you implement this particular? I mean, there is a famous data structure which you can use to solve this problem.
Mini heap.
What is it? It is a heap. Okay, in this case, it would be a min heap. Okay, and this particular problem comes as a sub problem in many algorithms. One of the famous one is Dikstra's algorithm. Okay, in Dikstra's algorithm, if you go inside and see, you will see that this is a sub problem there. You are adding some elements in an array. You can, I mean, this is an array, but there you use a heap itself. So you add an element in a heap, and you have to delete a minimum element from the heap. And this is a famous, this is a simple example where you will have to use a heap. And if you use a heap, we know that both these operations can be done in order log n time if there are n elements in the heap. Okay. Now let me ask you. So I just written them. There are two types of update, and both updates take order log n time, assuming that there are n elements in the heap. Okay. Now let me ask you another question. Okay. Again, this may not be so famous, but this is one of the dynamic problem. Okay. So suppose you are given an array A, and you have to perform the following operations. What are the operations? Well, the first operation is add I, j, in which you have to take the ith index in the array, and in that particular cell you have to add a j. Okay, basically add ai plus j, and then again you update ai. Okay, so this is what you have to do. And the second operation that you have to do is you have to find the minimum number between the ith index and the jth index in this array. Okay. Again, this is a dynamic problem because I will, at any update step, I can ask you to do any one of the following. I can ask you to add I, j. I will choose any index, and I will ask you to add some number in that. And the second thing which I may ask you to do is I'll ask you to find the minimum between any I and j. Okay. Now, I hope everyone can see that in an array, the first thing can be done in order one time, because it's just nothing, right? You have to just add a j at the ith index. So this can be done in order one time, but this would require order j minus I time, because I will go over all the indices from I to j, find the minimum. Okay. Can anyone tell me if you can do better than this? And if you know what is, there is an answer, what is the running time of that?
Sir, like we can pre-compute like I to j minimum in advance, and when there is an update, like if it happens to be lesser than the currently stored minimum, then we can definitely like change that.
So you are saying that you pre-compute n square values. Now the problem with this is when an update happens, you need to again maybe change. I don't know how many values you have to change. I claim that you will have to change at least n values.
Yes, sir, I get it. I think then we can use a segment tree like approach, I guess.
Okay. So I don't know what the segment tree is, but I'll tell you what the idea of segment tree is. Okay, so you'll use a data structure which is similar to a binary search tree. Okay, and I claim that if you do something like this, both these operations can be done in order log n time. So what is this? Okay, so suppose this is your array. Your array is 4, 5, 4, 7, 8, 1, 9, and so on. So what I'll do is I'll make a complete binary search tree for these 8 numbers, and I have used 8 numbers for a reason, because there are 8 leaves. Okay, and what I'll do is I will put all these numbers at the leaves: 5, 4, 7, 8, 1, 9, 10, 15. And now what I'll do is at the internal nodes in this leaf, I will put the following numbers. So here, in this node, I have the minimum of 5 and 4. Here I have the minimum of 7 and 8, and so on and so forth. So this is the second last level in the complete binary tree. And I'll just repeat this. So you'll have 4 here because this is the minimum of 4, 7. You have 1 here, which is the minimum of 1, 10, and so on and so forth. And you complete this full tree. Okay. Now, suppose this query comes, which is find minimum 2, 7, which is index 2 to index 7. And let's say index 2 is here, it is the number 4, and index 7 is the number 10. Okay. Now, can you see that you can actually use this particular structure in a very good way? Okay. Again, I'll be pretty vague here because this is, again, this is a problem that I don't know how many of you have solved or you have seen, but this is a problem that you may have seen. Okay. So what we do here is we move from, let's say the first number is 4. So we move from 4 to the least common ancestor of 4 and 10. In this case, the least common ancestor of 4 and 10 is 1. So I will move from 4 to 1. Okay. Similarly, on the other hand, I will move from 10 to 1. Okay. And now what I want to do is I want to choose some numbers that I would compare. Okay. In the worst case, I would have to compare these 1, 2, 3, 4, 5, 6 numbers. But I don't want to compare these 6 numbers. I want to compare some less number of quantities and give the answer. Okay. Now, one of the number is 4. I know that I have to compare this. The next number is 10, and I have put them in pink because I need to compare them. The other numbers that I will compare and I have put them in pink is 7 and 2. And that's it. I will only compare these 4 numbers, and I claim that the minimum of these 4 numbers is also the minimum between the numbers 4 and 10. Okay. And how do I know this? Well, what I'll do is whenever I go from the 4 to the root, and if I take a left turn, so now when I say a left turn, it is from the parent to a child. So this is a left turn. Okay. So whenever I see a left turn, what I'll do is I will include the sibling of this node 4. So for this node, there is this left turn. So I will include the sibling of 4 in my comparison. And I can do this because all the nodes which are in the subtree of this node, they are between 4 and 10. So instead of comparing these two, well, why do I compare these two? I already have the minimum of these two sitting here. So I will just use this. I will not use 7 and 8. I will just use 7 because I've already found this. Okay. And I claim that all these the numbers which are in the subtree of this particular 7, it is within this whole range. So I'm not going outside the range. I'm actually inside the range. So whenever you take this left term, you include the sibling. Okay. Till you go to the root. Okay. And this is only one such node because I will not use this. I will not use the. So you might say, why not use this? Because this is also the sibling of, this is also a left turn. And I should use sibling of this. Well, this I should not use because this one could have come from here. Okay, instead of 15, there could have been a 1, and I should not use this. So what I'll do is I will do this only till I am at the left child of the root. Okay, so I will do this thing, and there are only 2 nodes that I have to compare, 4 and 7, when I'm going from 4 to the root. Similarly, when I'm going from 10 to the root, well, I'll do the exact symmetric. I'll see where I'm taking a right turn. And for those nodes, I will include the sibling in my comparison. Okay, and that's it. In this case, you see that I have to compare only 4 nodes and I'll be able to give my answer, which is the minimum of these 4 nodes, which is 1. And in general, I claim that I would have to compare only 2 log n values. Why? Because log n values might come when I'm going from 4 to 1, and the other log n values might come when I'm going from 10 to 1. So there are 2 log n values. So the running time of my algorithm is order log. Okay. So I hope this is clear. I mean, this is a very, very simple algorithm. You might feel that this is simple, but actually I have used these algorithms and the ideas in these algorithms in many of my papers. It looks very simple. Okay, it's deceptively simple. The other thing, so this is just one operation that you had to do. The other operation was, well, at some index you add some number. So let's say at index 3, I want to add -5. Okay, so what I'll do is, well, I'll go to index 3 and I will add -5. So this becomes 2. And now this particular update is actually pretty easy. Okay, now you just propagate this number to the top. Okay, so you see whether this number is the minimum of 2 and 8. Well, it is the minimum of 2 and 8. So what I'll do is I will replace 2 here. Okay, so, and then you just go on. I'll compare 2 and 4. Well, this is the minimum. So 2 again comes here. Then I compare 2 and 1. 2 and 1, but now 1 is smaller, so there is nothing to be done. So this is the entire thing for adding, for the add operation. And I hope you can see the add operation takes order log n time. And there is one thing which I did not tell you. The height of this tree is order log n because it's a complete binary tree, and the number of leaves is, let's assume n, assuming there are n numbers in the array. Okay. So both these operations take order log n time, which is better than the trivial algorithm that we saw. In the trivial algorithm, add operation took order 1 time. The find win operation took order j minus I time. So this is actually better because it's just taking order log n time. Okay. So I hope now you see that even though I'm saying it's a dynamic algorithm, there is nothing special about this. At least I hope you see that at least in these 2 examples, these are problems that you might have seen. I mean, you might even have solved this problem in your data structure or algorithms or some competitive programming. Okay. Now let's come to a simple problem that you might not have solved. Okay. So both the updates takes order log n time. Let's come to a simple problem that you may not have solved, but it is still a simple problem. Okay, so let me define this problem now. So suppose you are given a graph G. So in a graph G, there are these 2 vertices S and T, and I will say that these 2 vertices S and T are reachable from each other if there is a path from S to T. Okay, and let's assume this is an undirected and unweighted graph. So it's for simplicity. Okay, it's a simple graph. Okay, undirected, unweighted, and there is S and T are reachable if there is a path from S to T. Okay, some path. Okay, not even the shortest one. There is some path. Okay. So given a graph G, and this is a very, very simple problem. I want you to just give an answer for this. Suppose I want to find if S and T are reachable or not. How would you solve this problem? And what would be a very simple algorithm for this?
BFS or DFS?
BFS or DFS. Okay, you just do BFS and DFS, build a BFS and DFS tree from S, and then you just check whether T is in this BFS tree or not, or DFS tree or not. Okay, and if you see that T is in the BFS or DFS tree, well, T is reachable from S, otherwise it is not. Okay, very, very simple algorithm. It takes order m plus n time because that is the running time of BFS or DFS, where m is the number of edges in the graph, n is the number of vertices in the graph. We will use just this notation henceforth. Now let me make a change. Suppose you are given a dynamic graph where at each step one of the following might occur. Okay, So what you are given is the add an edge. Okay, so when you say add an edge, what you have to do is you have to add an edge between u and v. This is the first operation that you have to do. Okay, and the second operation is, well, I will ask you whether t is reachable from S of. Okay, so this is just a query. Okay, so second is actually not an update. It is I'm just a query. Okay, but this is actually an update. When I say add an edge, you have to add an edge in the graph, and second is the query. And I hope now you see this is a dynamic version of this problem. Okay, and this dynamic version is slightly different. I mean, I'll tell you what is good about this dynamic version of the problem. The first good thing about this is the edges are only added in the graph. Okay, so you're not deleting something, you're just adding edges. So your update step is just adding an edge. Okay, and such a graphs are also called incremental graphs. Due to obvious reasons, it's incremental. You are just adding things. Okay. Okay. So now let me ask you now, what would be a very trivial algorithm for this particular problem that you might, I mean, anyone can try. How would you solve this problem?
Sir, like you can use this data structure called disjoint set to like store the graph.
Disjoint set. Okay. And
since we are not removing it, like any edges, then so you can keep maintaining several disjoint sets, and like you so basically you can get the leader of every u and v. Like I mean, we are querying s and t, right? So like so if we can get the leader of s and t, if they're pointing to the same leader, that means they're in the same disjoint set.
Okay, and what would be the running time of your algorithm?
The query would be like about login, sir.
The query would be the login, but what would be the running time of your, I mean, the whole algorithm? What is the running time?
I think it will be like for query it will be login, and even add edge it will be.
Okay, so let me ask you in some other way. Suppose I add m edges in the graph. Okay, what is your total running time? Total running time means across all the, so whenever I add an edge, your algorithm would do something. Okay, now across all the additions, what is your running? What would you think your running time is? You said that the query time is order login. I take this. Well, I take this. What would be a total running time? If you know disjoint union, and I'm impressed that you came to disjoint union. I feel that you can solve it using disjoint union, but which I want you to see. Okay, in disjoint union, I can actually give this query is for any two vertex I can give, and you will be able to give me the answer. Okay, but in this particular problem, I'm not asking you to I'll not ask you questions for any two vertices. These two vertices are fixed. I'm only asking you about these two vertices every time. So S and T are fixed, at least in this problem. Okay, but whatever answer you gave, it is actually much more general. Okay, but your answer is correct, but you don't know the running time. Well, let me just tell you, the running time would be m alpha n, where alpha n is the inverse
Ackermann function, I guess. Yes, sir.
Yes, yeah. So well, you are correct. You can do this, but you can do much better for this particular problem. Okay, because you need not. I mean, this. I'm not asking you. I'll not ask you query for all the vertices. My S and T are fixed. Okay. So this is a simple algorithm. I'll not go to the trivial algorithm because there is some other algorithm which I don't know what the name of the person is. Again, there is something from the chat. So I'll encourage you to just unmute yourself and say something, because Sometimes when I'm in a flow,
So my question is, should it affect the original problem? Because original problem, since we are not deleting any edges, the original problem would still be answerable.
Yes.
Right?
Original problem,
but the running time would increase, as you mentioned, by m plus alpha n, depending
Yes.
on the rate of additions of new edges.
My question is, can you do something better than m alpha n for this problem?
Something better than m alpha n?
Yes. Because m alpha n, that is a very nice algorithm. It works for given any two vertices, it will give you the answer whether they are reachable or not from each other. Okay, but I'm not even asking you that. I'm asking you from just for SNT. So if my query, in my query, if the two vertices are fixed, then it may be the case that you can do something better. It's not clear, but it may be the case. Okay. So one more algorithm that you can use, and I will just say this algorithm because this is always a trivial algorithm that you can always build, is that after you add an edge, you run the static algorithm again. So you run the static algorithm again. So this is called recomputation from scratch. Okay. So after each addition, you just run the static algorithm again, and you can always solve this problem. Okay, but the running time of this algorithm is very bad because there are m additions, and for each addition, roughly you will take order m plus n times. So this is the running time of BFS. So the total running time of your algorithm would be m square, which is very bad. Just now we saw m alpha n as one of the answer. Okay, even though I hope it is clear to some of you, but if it is not clear, then also it is fine. Okay, so now what we'll do is we'll try to solve this problem from scratch. I mean, not from should not say from scratch. It is not from scratch which I wrote here, but we'll not use disjoint set union. That also can be used, but the running time is m alpha n. So let's just see what we are trying to do. Okay, how will we will solve this problem? As I said, this is a very simple problem. So what I'll do is, first let me just tell you what happens in this particular problem. So an edge is always added in the graph, and let's say for at this particular point of time, edge BC is added, and there is actually nothing to do because at this point of time, S and T are not reachable. Okay, at next situation, maybe this edge is added. Again, there's nothing to do. Then this, then maybe this, and this, and at this point of time, your algorithm should say that S and T are reachable. And once S and T are reachable, they are always reachable because edges are only being added in the graph. They are not deleted. Okay. So once S and T are reachable, then basically your algorithm need not even do anything. Your algorithm can just stop because it knows that in the query it has also always have to say yes, they are reachable. Okay. So now let's see how we will solve this question. Okay. So what I'll do is all vertices that are reachable from S, I will color them black. Okay. So initially you can see that S is colored black. Okay. And now let's see what happens when an edge is added in the graph. Okay. So suppose an edge BC is added in the graph. I claim there is nothing to do, because my invariant is all the vertices which are reachable from S are colored black, and in this graph, well, I don't have to do anything. Okay, my invariant is true. Suppose, and then I add edge BT and ST again and CT, and again I claim there is nothing to do because my invariant is still fine. Okay. All the vertices that are reachable from S are colored black. Okay. Then I add an edge SA. And now what I'll do is I have to maintain this invariant. So what I'll do is I will color A black. But there is one more thing that I would do after I color A black. What is that? Okay.
All its neighbors also should be colored black.
Look at all the neighbors of A, and I should color them also black. But in this case, there is only one neighbor of A, and that is already black. So there's nothing to do. Okay. This my algorithm ends. This is my update algorithm. So my algorithm ends. Okay. Next thing is this edge is added. Again, what I'll do is I will color C black. And as I've told you, the next thing that you have to do is you have to look at all the neighbors of C and color them black. So I will do this. And you have to recursively do this for all the neighbors of B and T also. Okay. So you keep on doing this. And this is my entire algorithm. Okay. So this is a very simple algorithm. I will not even prove its correctness. I hope you see that this is correct. Okay, because once a vertex know that it is reachable from S, it will color itself black, and it will tell each one of its neighbor that now I'm colored black. You also better be black now. Okay, and if you think about it, okay, this is actually roughly what Bfs algorithm does, the breadth first search algorithm. Okay, just think about it. Okay. Okay, so now this is my initialization for this, and for all the vertices which are not S, I will color them white. Okay. And this is my algorithm for add edge. The first condition, let me ask you. Okay. Let's assume that I am adding this edge U and V, and it so happens that U and V both are white. Then what should I do? If both U and V are white and I have added an edge between them, what should I do?
Do nothing.
Do nothing. Nothing to do. Okay, no, because U is not reachable from V, V is also not reachable from V. Okay, and I have added an edge between them. Okay, there's nothing to do. Okay, same is the case when U and V are both black. They are already reachable. Okay, then there is nothing to do. The only interesting case is when U is black and V is white. Okay, so U is reachable from S, but V at this point of time was not reachable from S. But after I have added this edge, now V is reachable from S. So what I have to do is I have to color V black. Okay, but I will do this in a very specific way. And if you really see this specific way, you will understand that this is actually a Bfs algorithm. Okay. So what I'll do is I will add V in the queue. And if you remember Bfs algorithm, this is what Bfs algorithm does. It will add vertices in the queue, and I'll process this queue till it is not empty. Okay. So I'm processing this queue, and the first thing which I do is I will color V black because now it is reachable from S. Okay. And then I will go to each neighbor of V and tell them that now I am black, you also better be black. Okay. So for each neighbor of V, if the color of that neighbor is white, if that color of that neighbor is black, well, I claim that it cannot be black, because if the color of that neighbor was black, even V would have been black. So this line is actually not needed. Okay, so actually it is needed. It is needed because U is also a neighbor of V. Okay, so it is actually needed. So if the color of that neighbor W is white, well, now that neighbor should also be black, because even that neighbor is reachable from V. Sorry, it's reachable from S. So initially the picture will look something like this. So S is black. So this is S, and it is reachable to U, and U is also black. And I have added this edge in the graph. Okay. So the first thing that I have to do is I have to make this V black, and to each neighbor of V, say W, well, I have to color W also black. Okay. So basically I have to do I have to process W as I have processed V. So that's why I am putting W in the queue. Okay. So I put all the neighbors of V which are white in the queue, and this goes on and on and on till the queue is empty. So I hope you see that this particular code is actually a BFS code. It's a bet first search code where I'm starting from V and I'm only looking at white vertices. If I encounter a black vertices, I don't even add them in the queue. I'm just looking at white vertices and I'm then coloring them black.
Sir, will DFS work here as well? Like since you're just coloring it black.
So DFS should also work, I guess. Yeah, so DFS should also work, though BFS is much more clear to you. So the query is very, very simple. Okay, the query. So if you remember in the previous answer, the query time was order log n, but in this case, the query time is, you have to just see the color of T. If the color of T is black, then you return S, otherwise you return no. Okay. But my question is, what is the running time of this algorithm? I mean, the total running time. So I'm adding edges. I'm executing this procedure for all the edges that I have added. What do you think is the running time of this algorithm? So the query time is order 1. I hope you see this. But what is the running time of this algorithm? And the code is in front of you.
I think it's the same as BFS, sir.
But what is your logic? I mean, why is it?
Because we are going to be coloring the whole graph black, like as the edges keep coming. So and we won't be coloring it multiple times as well. Like
okay.
So essentially, we'll be doing like a graph traversal of the entire graph, like provided all the edges keep coming.
Okay. So the main thing that you have to see is that all edges in this graph, or let's look at a vertex V. All edges of V are traversed when V becomes black. Okay. So that is the place where I'm traversing all the edges of V. Okay. And after that, an edge VW is traversed only if this edge is added at that particular update step. Okay, else I'm not even traversing this edge. Okay, so my point is that whenever a vertex becomes black, at that point of time you are traversing all its edges. Apart from that, you will be traversing any edge of V only if that edge is added in the graph. Okay. So my claim is that the total running time, and I don't think this 2 is needed, the total running time of this particular algorithm, well, this is for initialization. Okay, is summation of degree of V. Why? Because whenever V becomes black, you are traversing all the edges of, and you are traversing an edge of V only once. Okay, the other time when you will be traversing is, well, when this edge is added in. So this is the total running time of your algorithm, and this is order n plus n. So the running time of this simple algorithm is actually same as the BFS algorithm. And if you look at this, this is a BFS algorithm, which I have just adapted this algorithm so that it works for an incremental graph. This is actually a BFS algorithm only. Okay, and this is what you have to do in dynamic graph algorithm. What you will have to do is you have to internalize the static algorithm by heart. I mean, it's not that you're just mugging it up. Okay, you have to internalize the whatever happens in the static algorithm and check if you can make it dynamic. Okay. If you can make it dynamic, well and good. Like this, I can make this dynamic, and this is nice. Okay. Sometimes you will be able to do it, sometimes you might not be able to do it. Okay, but at least you should know the static algorithm, each and every points of the static algorithm by heart. Okay, then only you will be able to do any research in dynamic graph algorithms. or for that matter, any and streaming algorithms also, online algorithms also. Okay, let's go to a slightly harder problem. Okay, so this problem is, yes, it's only a slightly harder problem. Let's assume that I've given you an undirected and unweighted graph G, and again a source S, but this time T is not fixed. Okay, and what I want you to do is I want you to find the distance between S to all the vertices of G. Okay, so my question to you is, how would you solve this problem in a static graph?
BFS, sir.
BFS. Okay, I hope you don't give an answer that this is, you can do it using Dijkstra's algorithm. Well, Dijkstra's algorithm will also give, because it's an unweighted graph, you can actually do a BFS. Okay, and once you have done a BFS from S, what you can do is you can then find the level of each vertex in the BFS tree, and it will give you the distance from S to that particular vertex. Okay. For example, if this is the BFS tree, then all the vertices which are at level 1, say A and B, they are at a distance 1 from S, C, D, E are distance 2, and F is at distance 3 from S. Okay. Now let's make this problem dynamic. Okay. Now in the previous problem, what happened was I was adding edges in the graph. Okay. In this particular problem, what I'll do is I will delete edges from the graph. Okay. So assume that you are given some initial graph, because the initial graph is not empty. Okay, so there is some graph which is given to you initially, and the first operation that you have to do is delete an edge E, which means that you have to just delete that edge from the graph. Okay, so this is the first operation. The second operation that this is not an operation, this is a query now. So I will ask you to find the distance from S to T in this graph. Okay, so these are the two operations, and again you can see that edges are only deleted in this graph. Such a graphs are called decremental graphs. Okay, so now again let's go back to you and let me ask you, how would you solve this problem? What is the trivial algorithm for this particular problem? I mean, any trivial thing that you can. Also, I should tell you one thing, which is about dynamic graph, that deletion is actually much harder than addition. Okay, so deletion of edges are actually harder to, those problems are harder to solve than addition of edges. Additions are slightly simpler. Okay, in the previous problem, just try to solve it for deletion of edges. So in the previous problem, I just told you that they are it's for only addition of edges, but try to solve it for deletion of edges. Those are not easy problems. Okay, so let me give you a trivial algorithm. As I said, the trivial algorithm is normally an algorithm which involves recomputation from scratch. Okay, so my algorithm would be pretty easy. Okay, after I delete an edge, I will run a BFS algorithm again from S. Okay, and my query is then very easy. I'll return the level of T in this BFS. So the query time is order 1, but deletion is very bad because I'm running my BFS algorithm again and again. So assume that you start with a graph which has m edges. So there are m edges which are to be deleted. So the and BFS takes order m plus n times. So roughly the total running time of this algorithm would be m into m plus n, because you are deleting m edges. So it will be roughly m square. Okay, so the point is, can you do anything better than m square? Okay, so let's see. Let's look at an algorithm which maybe it does better than m square. I don't know. Okay, so suppose this is your BFS tree. Okay, and the edges which are in red are there in the graph, but they are not part of the BFS tree. Okay. So there is an edge from A to B, there is an edge from A to E, and so on and so forth. Okay. Now let me ask you a simple question. Suppose I delete this edge, let's say E and F. Would you do anything? Would your algorithm do anything after you delete an edge E, F? Or should you do anything? This is what I should ask. I hope you see that there is nothing to be done if E, F is deleted, because the distance from S to E remains the same. The distance from S to F remains the same. Okay. Now remember, we want to find the distance from S to all other vertices. That's it. Okay. I'm not asking you all pair distances. I'm only asking you the distance from S to all other vertices. So if I delete an edge E, F, which is there here, the last red edge, well, then there is nothing to be done. I mean, the BFS tree does not change. Okay. So there's nothing to be done. The problem comes when you delete an edge which is S, B. Okay, let's say you delete an edge which is a tree edge. Okay, so if you delete SB or BE or so on and so forth. Okay, so this is where the problem will come, and the algorithm that we will see now will try to tackle this problem. Okay, so let's see. Okay, so what I'll do is I will maintain some data structures at each vertex in this graph. Okay, and what is this data structure? So each vertex will maintain the level of all its neighbors in this BFS tree. Okay, and this BFS tree will also be changing. So for example, in B will maintain this following information, that the vertex S is at level 0, vertex A is currently at level 1, vertex D is at level 2, and its last neighbor is vertex E, which is at level 2. Okay, and this information will be there. Every vertex will have this information, all the neighbors and what are their levels. Okay, so the neighbors might be in that, you might go to their neighbors via tree edge or maybe a non-tree edge, doesn't matter. Okay, but I'm maintaining this for all the neighbors of a vertex, and this, in this case, I've told you what is the information that B contains or that B has. Okay, and let's now assume that this edge SB is deleted from the graph. Okay. So SB is deleted from the graph. The first thing I'll do is I will delete this. In this data structure, I have maintained the level of S, but now S is not even my neighbor. Okay, so I'll delete this information from my data structure, from the data structure of B. Okay, the same thing you have to do in the data structure of S also, but let's look at B now, because B is important here. Okay, so now my question is, B was at level 1 because S was at level 0 and S was a neighbor of B. Now the picture is in front of you. In fact, I have written this. I should not have written this. But now what I'll do is I will find the smallest neighbor of B, or sorry, find the neighbor of B whose level is smallest. Okay, so S is gone. Okay, and I have these three neighbors, A, D, and E. I will find a neighbor of B whose level is smallest. Okay, so after I find such a neighbor, what should I do? Anyone? So I'll find a neighbor of B whose level is smallest. Then what?
It will be 1 plus the distances of all that in A, the neighbors of A.
What can you say it again?
If we are finding a neighbor of B whose level is the smallest, then we can get the neighbors of that by adding 1.
No. So look, my point is that B is now not at a distance 1 from S. Okay, in fact, the distance from S to B has increased. Can anyone? This is the whole graph is in front of you. Okay, because the edges which are not in the BFS tree, they are red edges. What is the shortest distance from S to B in this graph? Can you see it is 2? Okay, so in the BFS tree, B should be at a level 2 in this, in the BFS tree. Okay, so what I'll do is, once I have found a neighbor of B whose level is smallest, in this case, that neighbor is A. What I'll do is, I will make B the child of A. Okay, what I'm doing, I'm basically updating my BFS tree. Okay, my BFS tree looked like this when SB was present. Now SB is not present, so SB is deleted. Okay, so B cannot lie here. B, the level of B, I mean, as of now, B cannot lie here. Okay, the level of B should change. Okay, so B, why? Because it's none of its neighbor is at level 0. If any neighbor of B was at level 0, then B could have remained at level 1. But all the neighbors of B are either at level 1 or greater than 1. Okay, so what I'll do is, I'll choose a neighbor whose level is smallest, and that neighbor is A. So what I'll do is, I will make the level of B, so I will make the level of B2 and make A the parent of A. And now I claim that B is at its right place. Its distance from S is actually 2. It should be at this level.
Sir, are we maintaining this like distance information for all nodes?
So the level of a vertex will give its distance from S. That is the property of BFS tree, right? It gives you the shortest distance from S to any other vertex if the graph is undirected and unweighted.
Yeah. So basically, essentially, we're maintaining only one distance, right? Like from S, from
But
the
there is only one shortest path, right?
Yes, sir.
I mean, the length is all. There is a unique length. The shortest path itself, there are be many shortest paths, but the length is unique.
Yeah,
right?
length is one unique. Yes, correct.
Okay. So now B has changed. B is at distance 2, but my process still is not complete. There is actually a problem in this picture. Can anyone tell me what is the problem? There is some problem in this picture. Look at this edge. Okay, I mean, in a BFS tree, an edge should be from the parent to the child, or and the level of the level of parent should be less than the level of child. In this case, well, B and E both are at the same level. Okay, so this edge was perfectly valid in this picture, right? Now what has happened is that B has come to level 2. Now this edge still remains. So what should I do?
Push it down.
Push it down, but in algorithmic terms, what I'll do is do the same thing that I have done for B. Okay, so what I'll do is, for this particular okay, so before even that, okay, so what I'll do is, this is one thing that I have to do, so that's why I've written. So if the level of B is changed, I will tell each neighbor of B that its level, about its level. Why? Because, well, each person or each vertex is maintaining the level of its neighbor. Okay, so it stands to reason that whenever a level of a vertex changes, it tells each of its neighbor that, okay, now my level has changed, you better update. Okay, so this is one thing that B will do. Okay, it will tell each of its neighbor that its level has changed, and in this case it has changed. Okay, and for all the children of B, okay, what I will do is, I will repeat whatever I have done for B, which is I will repeat 1, 2, and 3 for each child of B in case the level of B has changed. And in this case, the level of B has changed. Okay. And there is only one child of B, which is E. Okay. So now what I'll do is I'll perform the same thing for E. So again, if you see E, E has this information that B is at level, not 3, it is at level. Oh, this is at level. Okay, I made some mistake. So let's say, so B is at level 2. So B is at level 2. A is at level 1. And which is the next, and F01 is at level 3. Okay, so this is the information that E has. Okay, now what E will do is, again, it will choose the vertex which has the minimum level. Okay, and which is that vertex? Well, A is that vertex. Okay, and it will make A its parent. So A becomes, so this edge is added in the BFS tree. This edge is deleted from the BFS tree. So that's why this edge becomes black. This edge becomes red, and the level of E has not even changed. The level of E remains same. So there is nothing to do after this, for at least for E. It need not tell each of its neighbor that what has happened to it, because its level has not changed and there is nothing else to do. But if the level changes as it was with B, then I have to do a lot of things. I have to tell all my neighbors that my level has changed, and I have to tell these especially to my children in the graph, okay, because their level may or may not change. Okay, in this case, the level of E might have changed if this edge AE was not there in the graph. Because this edge A is there, the level of E has not changed. But if this edge A was not there in the graph, then this vertex E, that vertex would have come to level 3. Okay, so I hope this thing is clear to you. If not, you can ask me any questions regarding this. Okay, what are we doing? Okay, so the first thing that we are doing is, whenever an edge is deleted, you start with that particular vertex. Suppose S is deleted, you look at, suppose V is the child of S, and this edge is there in your BFS tree. You find the smallest neighbor of, you find the neighbor of B, whose level is the smallest. Okay, make B the child of A. If the level of B has changed, tell each of its neighbor that now my level has changed. You better update your data structures and repeat this process for all the children of B if the level of B has changed. And this is my entire algorithm. Let's write this algorithm in an algorithmic form. Okay, so my initialization is, I will make a BFS tree from S. Okay. And suppose I'm deleting this edge UV. Okay. And let's assume that if UV is not even in this BFS tree, then I claim that I don't have to do anything. Okay, as we have seen. Okay, if this edge is not even, it's not a part of the BFS tree, you basically do nothing. As let's assume that U is the parent of V in this BFS tree. Okay. And now what you have to do is you have to start a process from U. Okay. So what do you have to do is, again, I'll be repeating this process for many vertices. That is why I'm using a queue. Okay. So I will add V to the queue. Okay. And I'll process all the vertices in the queue till it is not empty, till it is empty. Okay. So the first thing we do is we will find a neighbor of V which has minimum level. Let's say this particular neighbor is A. I will make A the parent of V. I will change the level, or now it depends what is the level of the A, but level of V will now be equal to level of A plus 1. Okay. And if the level of V has changed, look, it may happen that even after this operation, the level of V has not changed. Like we saw in this case, we saw for E, even its parent has changed, but its level did not change. Okay. So where am I? Yeah. So if the level of V has changed, then what I'll do is I will go to each neighbor of V and tell them to now you update your whatever you have. Okay. So basically you update the level of, okay, not level of V, level of V in the data structure at W. So W maintains some data structure and you basically update the level of V in the data structure of W. And for each child, and if suppose W happens to be a child of V, what I'll do is I will add W to the Q. And that's it. This is my entire algorithm. Is this fine? Okay. And if you have any questions regarding this particular algorithm, you can ask me. I mean, basically, whatever I told you pictorially that I'm going to do, that is what I have done. Okay. So you will process V like this, and you will also, if the level of V has changed, you will process each neighbor, each child of V also. Okay. Because the child of V, the level of V has increased. So what happens to their children? Well, their level may or may not increase. So you just process them and check.
Sir, where are we repeating that steps 1 and 2 and 3? Like,
yeah. Pardon?
Sir, like step 4, could you explain that again in this algorithm where it's happening?
What is happening? Can you say it again? What is happening?
Like repeat steps 1, 2, 3 for each child.
Oh, where is that happening? Okay, so where is that happening? The fourth step. Okay, so when I'm adding, if the level of V has changed, okay, I am adding each child of W in the queue. So for each child, again, this process will happen, right? Is this fine?
Yes, sir. Yeah.
Okay, so this is the fourth step that I have written here. So this is basically the fourth step that I'm saying that you repeat this for each child of W. Okay. Okay. So now query is very, very easy. And in all these algorithms, I did not tell you the correctness, but let's assume that this is correct. That is not a trivial part. Let's assume that this is the algorithm is themselves are correct. The query part is very, very easy. Okay, I'm basically maintaining a BFS tree. Okay, in this case, maintaining a BFS tree is not that easy because edges are deleted. But if you see, you are actually maintaining a BFS tree. When an edge is deleted, you are finding the new level for some vertices in the way. Okay. And the query part is then very, very easy. You just return the level of a vertex. Okay, suppose you are asking the distance from S to T. So your query is T, and you just return the level of T in the BFS tree, your current BFS tree. That is the shortest distance from S to T. That's it. Okay. So query is order 1 time. My question is, what is the running time of this algorithm? If you have understood and if you are with me till this point in the algorithm, what do you think is the running time of this algorithm? The whole algorithm is in front of you. Okay, I am not hiding anything. Anyone can make a guess? Guess is also fine. I'm deliberately taking this much time because I want to, because I cannot see you. So I don't know if you have followed till this point or not. But at least the algorithm is in front of you, and this algorithm looks very, very similar to the BFS algorithm. And if you have analyzed BFS algorithm on your own at any point of time in your life, what do you think is the running time of this algorithm?
V plus E only.
Not really. It's a wrong answer. Anyone else? So m plus n is not the correct answer.
So is that going to be v into v plus e?
Why that? Why is that? You are correct, but why?
So my rough thing is like we may need to keep updating this over and over again, and in the worst case we can do it n times, like
Okay, oh, but so you said we need to keep it updating. So you referred to some objects, but it's not clear what those objects are.
no sir, like I mean it was only a very rough intuition on
Okay.
what is happening, because we are doing a BFS and we may need to do this BFS for all n vertices, so that was my intuition.
Okay, okay. So your answer is correct, but your explanation is, I think, is wrong. Okay. But even though your answer was correct. Okay. But before we come to the answer, okay, let me ask you this following question, which we started with. Okay. So these are two operations that we do. Okay. You find a neighbor of V with minimum level, and this is another operation that you do. You update the level of W. Oh, this is not W, as I said, this is wrong. Update of the level of V in the data structure at W. Okay, what is this data structure? So if you remember, I told you that this is what I keep at each vertex. Okay, how will you implement this data structure?
A hash map?
No, not hash map.
Or an array?
Not even an array. I mean, it's a simple thing. We started with this heap.
Min heap.
Min heap, right?
Yeah,
I mean, min heap. So you do this with a min heap, and that's why at least at this step the running time would be order log n. Okay, I claim that all the other steps are order 1. Okay, at least inside this while loop, and this while loop is is where we need to calculate the time. Okay, so here we'll use min heap. Okay, and the main observation is the following, that whenever the level of a vertex changes, if you see in this while loop, the main thing that I'm doing is I'm telling each of my neighbor that my level has changed. Okay, and if my level has not changed, I don't even do anything. If my level has not changed, then the running time is just order log n. Because this is log n, this is order 1, this is order 1. And if my level has not changed, then I don't even do anything. So these are actually pretty good cases. I'll just come out. Okay. But the bad case is if my level has changed. Okay. And if my level has changed, then I will go to each of my neighbor and tell them that my level has changed. And those neighbors will then update their data structures. And some of those neighbors might be my child. So I will add them to the queue also. But basically, this is the main step. This is the most time consuming thing, that I'm telling everyone that my level has changed. One more thing that you see, and I hope you see this, because this is a very, very important thing about this particular problem, that the level of a vertex can only increase, it cannot decrease. Because this is a decremental graph. Edges are only decreased, or edges are only deleted in this graph. So the shortest path between S to any vertex can only increase, it cannot decrease. So the level of a vertex can only increase, it cannot decrease. And whenever a level of a vertex increases, it tells each of its neighbor that my level has increased. Okay. So when the level of a vertex changes, it tells each of its neighbor, and I claim the running time there is degree of v into log n. Well, this log n comes because of this data structure, okay, because of the mean heap. So it is degree of v. So because I'm going to each neighbor and I'm telling them, okay, my level has changed. Okay. So when the level of a vertex changes, this is the running time that you are incurring. Okay, this is very, very important, and this is the way BFS algorithms are normally analyzed. Okay, but how many times the level of a vertex can change? Anyone? I have already given this answer. How many times a level of a vertex can change in this entire algorithm? Anyone? So the levels can only increase. Okay. So how many times the levels can change? What is the maximum distance between S to any vertex?
N minus
N,
1.
right? So can you see the levels can only change n minus 1 times, right? Because the levels can only increase. It means that the running time of this algorithm is, well, the number of times the level can change. So this is the number of times the level can change. This is the running time that I'll incur when my level changes. And this I claim is the total running time of this algorithm. I mean, this is the dominating factor in this particular problem. There might be other things, but they are very small compared to this running time. Okay, this is a major bulk of this algorithm is basically whenever my level change, I tell each of my neighbors. And that is the worst part of this algorithm, but still it is not it's not that bad. Okay, if you do this calculation, you will see that this running time is mn into log n, because summing the degree of each vertex, that is order n, where m is the number of edges in the graph. Okay, so this is mn into log n, and basically you can also improve this further to order mn using something, well, this trick is very simple, but you can also get an order mn time algorithm for this particular problem. Okay, and if you remember, the trivial algorithm that we saw was order m square. Okay, and the algorithm that we saw just now is order mn. So this is actually a slightly better algorithm, and this is one of the famous algorithm in dynamic graph algorithm. This is due to Evan and Shiloch in, I think, Journal of ACM in 1981. A very famous algorithm. Not only is this algorithm very simple, there is one more thing about this algorithm is that it is nearly optimal. You cannot do better than this. So order mn is actually the best that you can do for this particular problem. What is the problem? A decremental graph, and you are trying to find the shortest path. You are not trying, you are maintaining the shortest path from S to every vertex. Okay, so the total running time of your algorithm is order mn, and as I said, this is a famous algorithm by Evan and Shiloch. Okay, so I think I am actually out of time. What I had prepared for this particular talk was one more problem, which is previous. I mean, just now you saw single source shortest path because the source was fixed. Well, what happens when you have all pair shortest path? So you want to, your query would be the following. Okay, so again the first update is same, you delete an H in the graph, but your query is now following. You find the shortest path from U to V, where U and V can be any two vertices in the graph. So your source is not fixed. Okay, so this is that was single source shortest path. This is all pair shortest path. Okay, so that is also what I had prepared, but I will not do that. What I'll show you is the result, which is very surprising. Okay, so I prepared all this, but I don't have the time to go through all this. But I'll go to the result. So for all pair shortest path, there is an algorithm with total update time m and log square n. Okay, so if you remember, for single source shortest path, even and Shiloch algorithm, the algorithm running time was order mn. Even for all pair shortest path, the algorithm's running time is not that, it has not increased that much. Okay, but the query time has increased. So this was the update time, total update time. And the query time for that particular, for SSSP, so this is SSSP and this is APSP, all pair shortest path. The query time was order 1, but in this case, the query time is order n log n, but we can also decrease this query time. Okay, that I have not written and I did not intend to do also. But you can decrease this query time also. And it's very, very surprising that single source shortest path, well, total update time is order mn, but even all pair shortest path, it looks like a bigger problem because your query is between any two vertices in the graph. But still the total update time is order mn. Query time is big, but as I said, you can also decrease. Okay, so I hope you have got a flavor of what dynamic graph algorithms are. Okay, there is only one thing which we did not do. Okay, which are fully dynamic graph. So what are fully dynamic graphs? Okay, or fully dynamic, well, if not graph, any dynamic problem. So in this, the two problems or three problems that we saw, the graph was either incremental, edges were only added, or decremental. Okay, but it may be the case that edges are deleted or added in your graph. Okay, so both the cases are happening. At any update step, I will add an edge in the graph, or I may delete an edge in the graph. Okay, those graphs are called fully dynamic, and those are the hardest graph problems to solve. Okay, and I want so I have not done any example of those kind of problems. I have done only incremental graphs and decremental graphs. Okay, so my time is nearly up. I will not do anything more from now. I mean, I'll not do anything more. But if you have any questions, you can ask me now.
So what was the other kind you mentioned? I did not hear you. Like incremental, decremental, and
Fully dynamic.
fully dynamic.
Yeah. So both edges are all maybe added and it may be deleted.
Okay, okay, got it. So, yeah.
Okay, and those are very pretty hard problem. Okay, even the problems that I have told you, single source shortest path, fully dynamic single source shortest path is it's not that easy.
I think I may have missed, in case you have talked about a textbook or two at the beginning. Do you have?
Unfortunately, there is no textbook as such for dynamic.
Okay.
I myself have never looked at any text.
So Manoj, what are the other questions that look like? For example, have we looked at kind of using ideas from two different type of algorithm design paradigms, like approximate dynamic algorithms, or I'm pretty sure randomize. I mean, there are questions where you look for an answer.
So this problem, which I did not have the time, had some randomization there. So in most of the dynamic graph algorithms, randomization would be crucially used. And I think that is true for most of the algorithms these days. Right. So randomization is actually an integral part of dynamic algorithms. Okay, so it was there in this third. I was actually worried that I will have to do something more, but even I was not able to do this. So yeah, so it is there. So, and your other question was approximation algorithms. Again, you can solve them in a dynamic paradigm, but the problem is this is what I feel is the problem that are solvable in the dynamic environment, at least the static algorithm for those problems should be easy. Okay. So I took shortest path, connectivity. Okay. If you see the dynamic versions of these problems, they are not easy. Okay. Even like last 10 years, if you see, you will see Stockfox soda papers on dynamic shortest path and all these things. Okay. Even matching is slightly easier, is also easier. So the problem that we have solved till now are connectivity, shortest path, all-pair shortest path, matching, independent set. Okay. And if you see, this is common theme that for all those problems, the static algorithm is, except for maybe maximum matching, for all those, the static algorithm is pretty easy. Even for maximum matching, we actually, the dynamic algorithms are for not for maximum matching, they are for some approximate matchings, like maximum matching or something like that.
Okay.
So because at least most of the time what we'll do is we'll try to somehow adapt the static algorithm, as I've done in today's lecture. But if your static algorithm itself is very complex,
okay,
then there's a very good chances.
And I also looked at some problems outside graph theoretic settings also, right? Like for example, I think there are some geometric algorithm which I remember seeing, the basic convex hull kind of things in dynamic
Yes,
settings.
but I have not seen them. Okay. So I have not worked on them, but yes, so you can ask the same problems on those questions also. So I normally work on graph problems, so I have not seen those problems. Yeah, but incremental convex hull, well, incremental convex hull is already there, but yeah. So you can actually, for convex hull is a very nice problem. So I really don't know on the top of my mind if there is any dynamic version of that.
Any more questions from the participants? Okay, so if not, let's thank the speaker. It was a wonderful talk, and okay, it's also the last talk of our the school. Avi, do you have something to add? Or
Yeah, Nicola have. Nicola will be adding it last.
It's okay. Okay, so in that case, I think let's conclude this session as well as conclude this summer school. I want to thank all the speakers and participants who are here, who was here till the last session, and yes, everybody. Also, I think Professor Srinivas Vivek is here. He's a co-organizer. Okay, maybe it's not here. Okay, and let me also thank all the student volunteers who helped in organizing, and also IIT-Bangalore for the support it gave. Okay, yeah, so okay, so let's hope that next summer school we have a physical school. But I hope all of you took the most advantage of even in the virtual settings. Okay, yes. Thank you, Professor Manoj.
Okay.